first session of the morning, so I appreciate it. First, my name is Guy Somberg. I am the client lead programmer at Extra Games. A little bit about me, I've been in games since 2002, so my video game career is just now getting its driving learner's permit. I've owned the audio engine at just about every company I've ever worked at, either for the whole company or just for the game I was working on. And I've shipped lots and lots of games and lots of audio engines, everything from AAA to small indie titles and kind of everything in between. So today, I'm going to show you how we work with audio in video games. Start with some audio fundamentals, give you an as-if model of what's happening in an audio device. This is kind of close enough to the truth to be, for the purposes of this talk. I'm going to talk about what the current state of the art is in game audio programming and move toward a standard C++ audio library, what that might look like. Now, the fundamentals are kind of not necessarily the things that we're doing day in, day out. Some of us are, but many of us are not. But they are nevertheless things that we're expected to have like background knowledge as a game audio programmer. Let's jump right into that. Here's a speaker. We have an electrical wire that we send electrical signals down. There's a coil that makes a magnetic field that moves a magnet that is attached to a cone. The cone vibrates, pushing the air. The air travels, the vibrations move through the air to your ear, and that's how you hear what's coming out the speaker. Now, if we graph the position of that speaker cone over time, you get a curve. And if we want to replicate the same sound, we just have to replicate the curve out the speaker. The problem with this curve is that it's an analog signal. We have to move the signal a certain amount over time, but a computer is very much a digital, discrete entity. So in order to work with digital signals, or to translate this to a digital signal, we sample it. And when you sample audio data, it's called pulse code modulation, or PCM. So if you hear me referring throughout this talk to PCM data or uncompressed audio data, that's this. This is pulse code modulation. Typical sampling rates for video games are 48,000 samples per second. Sometimes you'll hear 44,100. You'll also sometimes see lower numbers like 32,000 or a little bit higher numbers like 96 or even 192,000 in rare cases. But either way, it's going to be in the mid to high tens of thousands or low hundreds of thousands of samples per second. So by sending this data out to the speakers, we can play one sound, which is not very exciting. So let's see how we mix together multiple sounds and create a whole soundscape. Let's say we have the blue curve on the right and the kind of like puke green curve on the left. We want to play those guys together. What is that going to look like? It turns out it's this orange curve. We just sum up every point along the curve, sum them up together, and play that out. And that is exactly the correct curve. Write that out mathematically, it's just like this. The output signal is the sum of the two input signals. But because the output is itself a signal, we can now trivially convert that to this. The output is simply the sum of all the input signals. So now we have a way to play single sound, multiple sounds together. How do we actually get it out to the output device? And here's an as-if audio device. I'm not an artist, so it was the best I could do in PowerPoint. We have on the right-hand side sorry, that's the left, I realize. On the left-hand side, yes, a speaker. And in the middle is a digital to analog converter. This is your sound device, your sound card, audio card, goes by various names. And on the right, now I have to reverse what I see on my screen. On the right.
We're looking the same way as you. So it's right.
Thank you. Not supposed to turn it back to the audience. So reverse everything I just said. On the left, thank you. On the left is the kind of operating system's representation of this. It takes the form of a ring buffer. Here I didn't have enough time and I didn't have enough patience really to draw it as a ring buffer. So it's just a double buffer in this case, which is really a ring buffer of size 2 if you think about it. And so you're expected to be writing into the red buffer while the digital to analog converter, the sound device, is reading from the purple one. So it reads from the purple while you write to the red, switches, and reads from the purple again, and the switch again. Yay for my PowerPoint skills. So the thing about this is that this happens no matter what, whether you're ready for it or not. The number 0 rule of audio code, this callback that is triggering, that is asking for these buffers, waits for nothing. And so in 2015 at CppCon, Timur Dumler, I hope I said that name right, did this talk, C++ in the audio industry, where he goes into great detail about this very subject and how to write code for this very, very high performance, low latency environment. And so I'm not going to cover all of that, but I do want to, at the very least, I'll wait for him to do his QR code scanning, at the very least, summarize that talk in kind of one slide. So I encourage you to watch this, but here's the one slide summary of kind of what he was saying. In order to provide this, this callback with its buffers and have no errors, we have to guarantee that, we have to provide a number of guarantees, and we have to provide that the function will return in some time less than the length of the buffer that it's trying to fill. So if I have a 512 sample buffer at 48,000 hertz, that gives me 10.6 milliseconds to fill that buffer. That's less than the length of a 60 frames per second frame. And 512 samples is luxurious. A lot of times you'll have 128 or even fewer. So you have single-digit milliseconds to fill this buffer. We have to guarantee that we finish processing the whole buffer. We can't exit early and then come back to it. Once you finish, it's gone. We have to guarantee the output contains all valid audio data. So typically this will be either signed integers or floating point numbers in the range -1 to +1. And we have to guarantee that there are no errors or exceptions. So to provide these guarantees, we have to do a few things. First, we have to run our mixer thread at the highest operating system priority that is available to us. We must also never ever block the mixer thread for any reason. So that means you have to make all your algorithms either lock-free or ideally even wait-free. So to provide the no block guarantee, we can never do any memory allocations, no deallocations, and no I/O of any kind. So there's just some very strict requirements on the properties of this thread. So by outputting, so this is how we output the actual mixed audio data out. Now I've talked about how we mix it and how we play the audio data, but I haven't really talked about where audio data comes from. So video games are a high-performance, real-time application. And so the trade-offs of memory size, CPU cost, and disk I/O are very important to us. So we have to have a number of different options of how to represent, or how to be able to get our audio into our engines. Excuse me. The first option is just to decompress the file in memory. So we have a file on disk usually, and it's in some sort of compressed format, like MP3, OGG Vorbis, FLAC, ADPCM, the list goes on and on and on. And we load that into memory, we decompress it, and we end up with a buffer of PCM audio data. And when we load it this way, it's referred to loading it as a sample. We can also, rather than decompress it, we can store it in memory as compressed data. And what this means is that we have to decompress the data on the fly in that mixer thread. So we have a lot of strict requirements now about which formats are available to us, because in order to decompress it, we have to provide all those guarantees, the hard real-time guarantees, no allocations, no deallocations, no I/O. Not every format can be decompressed that way. So we have to limit the number of formats. And the advantage here, though, is that if we are willing to spend the CPU cost, which in general we are, then we have reduced our memory requirements drastically. Third option is if we have a memory buffer that we've gotten from some source. Maybe we loaded it from disk ourselves, maybe we got it off the network, maybe we got it from a microphone, maybe we got it from, I don't know, anywhere, a device of some sort. We can take that and copy it into our audio buffer, into our audio engine, or alternatively, we can point to it from outside the audio engine. But then we have to provide some lifetime guarantees about that buffer. 3B, we could do the same thing with a compressed buffer. If the buffer's in FLAC or some other compressed format, we can point to it or copy it in that compressed format and treat it just like we did if we loaded it from disk. Option 4, we can stream the data off of disk. So what this does is creates a double buffer of audio data, and just like any double buffer, you're consuming one side while you're writing into the other side. And the advantage here is that now when a file gets large enough, so it's larger than the size of that double buffer, now it can become more worthwhile to have the expense of the disk I/O to exchange memory for disk I/O. So you often see this with large files like music, long ambiances, stuff like that. A good rule of thumb for the typical sizes and lengths and compression ratios for video games is that if a sound is 10 seconds, give or take, then it might be a good candidate for streaming. It's just a rule of thumb and depends on the platform and all the other settings. The last option is a synthesizer. You can actually fabricate audio data from whole cloth using an algorithm and maybe some small amount of buffer. And we hook that directly into the mixer thread. So again, the algorithm that's generating the audio has to be real-time safe, but so long as you can provide that guarantee, then you can generate your audio data on the fly. So if you look at the right-hand side of all those options, there's really only 4 different things that you saw. That we have a buffer of wave data, either compressed or uncompressed, or a non-owning buffer of wave data. We have the file stream, and we have some code. That looks like, kind of like this. Although you couldn't actually use this. This is a simplification, but you get the idea. This is the backing store for our audio data. Or something that looks like this in some vague way. I want to take a step back at this point and ask, where are we, right? So at this point, we can load audio data. We can play as many sounds as we want together and output them to the sound card. So the question is, what now? What else is there to do? Now the work begins. I haven't even talked about resampling and clipping. I don't have time to do that today. This is, you cannot even start unless you implement resampling and clipping in your audio engine. Video games are usually 3D constructs, so we have to have some sort of 3D panning mechanism. Historically, that's been a vector-based amplitude panning algorithm, but these days with VR, we're moving into a lot of ambisonics, stuff like that. 3D attenuation sounds simple on the surface, but has a lot of subtleties. Submixes are another important feature where you can have some audio data that is mixed together with other audio data, and then creates a mix point where you can apply effects such as reverb or filters, and volume adjustments, and then send that off to another submix and onto another submix. Effects that I just mentioned, low pass filter, high pass filter, reverb, echo, all these kinds of things. There's a ton of work still to do. Now, if you're using middleware, some, but not all of this will be taken care of by that middleware. So there's just, at this point, that's kind of the fundamentals. I want to switch gears now and talk a little bit about the current state of the art in audio. Every operating system has some way of communicating with the sound device. On Windows, we have Wasapi and ASIO. On iOS and macOS, we have Core Audio. Linux has Pulse Audio, OSS, and ALSA. Android, the default is OpenSL. Just every platform, if you're on a console, they'll have their own stuff. Every platform has this. But these are really, really low-level APIs. These are providing you with an opportunity to fill that buffer yourself and do your own mixing. And so they're very important APIs to have, but video games, we don't want to live in that space. We want to live much higher, typically. So in video games, middleware is king. Fmod Studio and Audiokinetic-Wise are the big middlewares in like the Americas and Europe, that kind of zone, and CRI ADX2 is the big middleware kind of in China, Japan, Asia, that zone. If you're using Unreal Engine or Unity Engine, they'll have their own audio APIs. And the nice thing about these middlewares is not just that they're providing a wrapper for the different operating systems and their low-level API. It's not just that they're providing file I/O and sample decompression and streaming and all these other wonderful things, because they do provide those things. The nice thing about these middlewares is they're actually providing tools to the sound designers to allow them to express themselves in extraordinarily powerful ways. This is Fmod Studio, and what you're looking at here is a music event. And this music event has a low, medium, and high intensity section to the track. This is a single wave file that is being streamed in with these different intensities. It has different loop sections for those intensities. And there's an intensity parameter that automatically, as you move the parameter, it automatically transitions on the next beat to the desired intensity with a musical stinger to hide any transition effects. And all of this complexity is exposed to the programmer API through a single play event call and an exposed set parameter call. All of that. This is Audiokinetic-Wise. What we're looking at here is an event for a glass bottle impacting a surface. This event switches which sound it's playing based on the hardness of the target surface, and then applies a low-pass filter, a pitch adjustment, and a volume adjustment based on the force of the impact. And again, all of this is exposed to the game through a single play event call and a couple of exposed parameters to tell it what the hardness of the surface is and the intensity of the impact. This is CRI ADX2. I am less familiar with this tool, but I'm pretty sure what we're looking at here is a music track, again, with parameters to adjust volume, pitch, low pass filter, stuff like that. So given the fact that we have these tools, these extraordinarily powerful and expressive tools for the sound designers, what is it that we as game audio programmers do all day? There's, are we just hooking stuff up? What are we doing? So to answer that question, we have to ask, what kind of audio programmer are you? There's lots of different kinds. Now, this is actually a relatively recent development in game audio programming, that there's more than one kind of game audio programmer. These days, there's a technical sound designer who is a sound designer. This person is a content creator, but they have the ability and the technical know-how to go in and create hooks and implement features where they need to. We have the audio engine programmer who is kind of living in the space between the audio middleware and the game and creating and maintaining the audio engine logic and the tools surrounding that logic, interacting with the middleware code, the game code, and working closely with the sound designers to make sure that the features that they need are available in the engine. At a lower level, we have what we might call a DSP programmer who is implementing some custom effects, maybe some custom mixing techniques like frequency space mixing, that kind of stuff. And this is just the things I came up with off the top of my head that fit on one slide. There's lots of other ways to be an audio programmer. So my perspective is this. I'm the audio engine programmer. I have lived my entire career in that space where I'm providing services to the sound designers and creating that audio engine logic. So the kinds of things I'm doing are colored by that perspective. So here's the kinds of things we do. We set up game hooks for the sound designers. Just have they have a sound, they need to have some place to put it into the game, some hook to attach it to. Number one bug that every audio programmer ever has to deal with is why are sounds not playing? I actually fixed a bug, a why is my sound not playing bug last week. True story. We have to understand the tools that our sound designers are using in depth because sometimes they'll want to express something very complicated and they can't do it themselves, so we have to be able to go in and show them how to use the tools to do that. Sometimes we'll go in and take the role of a DSP programmer, implement some custom effects, maintaining the audio engine logic, writing and maintaining that. And ultimately, we're working closely with the sound designers to unlock their creativity. And we do this using C++. Here's some code from my current audio engine. And so this is code where we have a playing event handle, which is a wrapper for a playing handle or playing event. And the idea is that the playing event can get garbage collected effectively. Now, it's not actually garbage collected, but it can get removed out from underneath. And so the API surface is the same between the handle and the underlying object. And we have to guarantee that if the object is valid, that we forward the function call, otherwise it becomes a no-op. And so this is the function that you see. We're getting the playing event, checking to see if it's null, and then forwarding on the function. On this one slide, I realized, I counted, I have 7 modern C++ features. We've got variadic templates, we have a using declaration, we have stood result of, we have forwarding references, auto null putter, and stood forward. Also, this slide is using smart pointers, but they're not standard smart pointers, so I can't really claim them as a modern C++ feature. Also, in writing this slide, I discovered that stood result of is actually deprecated in C++ 17, which I did not know until, as I said, making this slide. It's deprecated in favor of stood invoke result, which has a little bit cleaner syntax and a little bit more power. In my current code base, I only have access to C++ 14, so once we can upgrade, I'll upgrade the code. Here's another example. This one's straight out of Unreal Engine. This is enqueuing this lambda to be called in the mixer thread from outside the mixer thread. And this is a much simpler example, but as you can see, we're kind of embracing C++ and using its functionality and features. So at this point, I want to bootstrap. I want to show you what a game audio engine looks like. I'm going to be using the Fmod Studio low-level API, and I'm going to start with a minimal sound playback example, and I'm actually going to be doing live code. We'll see how well this works. Here we go. Visual Studio with nothing in it. The only thing I've done here is set up the project to link against the Fmod Studio low-level API and set up the the directories for everything. So here we have to include fmod.hpp in order to get started. And first thing we need to do is be able to communicate with the audio device, which we do by having a system object. We allocate memory for the system object by calling system create. And then we still have to call system init, for which we'll pass in some default parameters. Null putter. OK. Now we want to load a file off of disk. We do that by loading it into an fmod sound object. And we load that sound object by calling system create sound. We'll go ahead and pass it the name of a file on disk. If I could type. And it goes paren quote. Pass it some mod default and some other parameters, and we'll have it fill in that sound object. So there we go. Now we've loaded sound onto disk. We play it then into a channel object. Channel is holding the data that we're loading. And we do that by calling, or the data that we're playing. This is actually the currently playing sound. We do that by calling play sound, surprisingly. We give it the sound object, some default parameters, and filling in the channel object. The only last thing we have to do is just wait for the sound to finish loading, or to finish playing, rather. So we say channel is playing. And although technically we don't need to, it is more correct to update the system object. So there we go. What is that? 25 lines of code. And we'll update it, or we'll compile this. So yes?
What do you mean by update the system object?
The system object, so in this example, I didn't need to. The system object updates gives you callbacks. It gives you does some processing for, I think, some 3D positions. And if you read the documentation on Fmod, they actually describe what the system update does. So I tend to just do it because it's good kind of practice when using Fmod. But like I said, in this example, it would work just as well without updating the system object. There's also modes in Fmod that are non-real-time modes where the mixing happens inside of updates. So if you want to do offline processing, stuff like that. All right, let's see if I can get this back to a working state. And then I have to do that and, oops, that. Yes. All right. So let's build an audio engine. And I'm going to go about 99% light speed because the purpose of this is not to go through it line by line, but to show you the shape of it, what it looks like. Now, of course, I have no idea how far through my talk I am, but that's all right. That's what you're here for. So here's the interface for the audio engine. We've got an init, update, and shutdown functions for kind of static initialization and update. We have functions to load and unload sound, set 3D listener position, some jukebox functions, play, stop, pause, that kind of thing, and some functions to adjust channel parameters. We're going to use the Pimple idiom here. Here's our implementation. And the backing store is a map of sounds and channels. Update function is more interesting than the constructor and the destructor. We have, first we check to see if the sound is finished playing, add it to a vector of iterators. We erase from the channel map any channels that are finished, and then update the system object. Load sound and unload sound are matched pairs. First we check to see if the sound is already loaded. Then we either load or unload the sound, and then we add or remove it from our backing store. Play sound, a little bit more complicated, but not too bad. We've got our, first we check to see if the sound is loaded. If not, we load the sound. Then if we fail to load because the file didn't exist, or there was some error in loading it, it was in a bad format or some corruption, then we exit early. Otherwise, we play the sound and set up all of its parameters. And I want to point this particular chunk of code out because we're going to see it again. And note as we're playing sound, setting parameters. That's all, just calling that section out. The rest of the functions all follow this pattern. We check to see if the channel exists, and then we set a parameter on it. They're all boring. They all follow the same pattern. All in all, it's about 250 lines of code, and you've got an audio engine that features sound playback in 3D, volume control, and some simple jukebox functions plus whatever other kind of parameters you want to set. But the problem with this, 250 lines, is that it's really hard to add new features. So to add new features, we kind of need to organize it into a state machine. And I'm going to show you one state machine that has worked very, very well for me across many, many games. I've shipped lots of games on the state machine I'm about to show you. And to build that state machine, I'm going to show you 3 exemplar features: fade outs, async loads, and virtual sounds. There's an asterisk next to virtual sounds because unfortunately today I don't have enough time to talk about what virtual sounds are. I'm including them here for completeness, but unfortunately I'm just going to have to gloss over their implementation. So I'll cover them just very briefly. If you think back at that code that you saw, the audio engine, or the state of a sound, any given sound, is that either it's playing or it doesn't exist, which makes the state machine for that engine look like this. This is the entire state machine. So if we want to add fade outs, we're going to add a state to track the fade out time and mark that we're no longer playing this, and then mark it as stopped, so that when this fade out is finished, or when the sound is stopped playing, we have the stopped state. And that's it. By adding these 2 states, we've implemented fade outs. To implement async loads, now we have to do a little bit more, because we have to, now there may be some length of time while we're waiting for that sound to load. So we have an initialize state where we can do kind of one-time initialization, a to-play state where we are actually trying to play the sound if we can and if we should, and if not, then if the sound is not loaded, we'll move it to the loading state. When it's finished loading, we'll come back and then continue through the state machine. Note that on the left side, yes, on the left side, there's that arrow straight from to-play to stopping, because now there's some non-zero length of time between when the sound was requested to play and when it is actually playing, especially if the sound was not loaded from disk. And at that point, you can already get a stop request for that. It might even happen on the same frame. So we jump straight to the stopping state. For the virtualization, again, I'm going to kind of gloss over it. Virtual sounds are sounds that are important enough to keep track of their existence, but they're just not important enough to actually hear. And if you want to hear more about virtual sounds, come talk to me afterwards. I'll be happy to wave my hands and enthuse about them forever. So this is the state machine. You can ship AAA games, you can ship tiny games on this state machine. So let's go ahead and build the code for that. I'm going to go a little bit faster, 99.9% light speed, because again, the purpose is to show you the shape of the code more than go through it line by line. Here's our interface. It is almost the same as before, except we have this new section here where we're registering and unregistering sounds that can be loaded. The thing about this is that it's fake. You wouldn't actually have these functions that look like this in your code, because in a real game, you'll have a spreadsheet of listing all this information, or you'll have a database of some form where you'll know which sounds are available through some other mechanism. But if you wanted to use this, you could ship on this. This is legit code. It's also boring, so I'm not going to bother showing any boring bits. The rest of the interface is all the same, except notice here on the stop channel call, we have a fade time, and the update gets a delta time seconds. All right, I lied about not showing any boring bits. I did want to show the load sound call, because this fmod non-blocking flag is the magic that makes async loads work in the fmod Studio API. This is our channel object, which is more complex by virtue of the fact that it exists in the first place. In the previous audio engine, we just stored the fmod channel object. Here we have an object that holds a channel object, among other things. Note, here's our state machine. The state is per channel. We have our backing store containing all the volume and sound and state and all these other things, and some functions to update and helper functions for the update. Play sound is now much simpler. All we have to do is allocate memory, and the state machine takes care of moving the sound through the state, through its life cycle of playing it and all that other stuff. Stop channel is the same if there's no fade time, but if there is a fade, then we just mark it as stop requested, begin the fade, and the state machine takes care of the rest. All the other channel functions are basically the same. They're still boring, but they're boring in new and exciting ways, because now instead of finding the channel object and setting its value, we're just setting the parameter, storing the value, and the state machine will take care of the rest. So here's our update object, or here's our update function, which is almost the same, except inside of the update, or inside of this loop, we are updating each channel and checking to see if it's stopped. Or checking to see if it's in the stopped state, rather. If we introspect that update function, it takes the form of a giant switch on state in which a miracle occurs. And if we introspect the miracle, we get a wall of code, for which I'm sorry, but I'm going to go through it step by step here. First, there's this initialize state, which in this example just has a single fall-through attribute statement. There's nothing there, it's just falls through. But this is a hook for adding new features. If you need to do any kind of one-time initialization on your channel, this is the place to do it. So if your sound designers come and say, I want to do one-time randomization of the pan and the pitch and the volume, that's where you do it. So then we move on to the to-play state, and here, first thing we need to do is check to see if we should even bother playing the sound at all. First, we check to see if it's stopped, we check to see if it should be virtual, and we check to see if the sound is loaded. If it's not loaded, we jump to the loading state. Then we play the sound and set its parameters. Note, these are the same functions as before. The only difference is they have all the state machine chazarai around it. And then we move on to the playing state. So the loading state, very simple. We just check to see if the sound is loaded. And if it is, we can go back to the to-play state, which will do all the logic to see what it should be doing. During playing, the sound is already playing, so we need to update its channel parameters, its volume, its 3D position, its pitch, anything else that is coming from the game engine. And then we just check to see if it's stopped and if it should be virtual. It's already playing, so we don't need to do anything else other than updating its parameters. For the stopping, we update the fade out, and we still need to update its parameters because maybe you have a very long fade out. The sound can still be moving around in 3D space. It can still be doing all the other things that it does while it's fading out to stop. Other than that, we just check to see if it's stopped and should be moved to the stop state, which is the world's most boring state. Here's the code for the virtualizing stuff. I'm not going to go through it, but you can see it has the same shape. We do some updates. We check to see if we should be transitioning to a new state. And I'm only showing it for completion. All in all, there's about 600 lines of code. And most of the difference between the previous engine and the current engine is that it's the state machine logic. But now, so we started with the same features as before. We've added those 3 exemplar features. But now the most important thing we've done is we've added hooks for adding more features. As the sound designers come and say, I want to do this, I want to do that, I have this crazy idea, now it's easy to add, whereas before it wasn't. Now, what we just saw is mostly game engine code, and abstracting the operating system API is done by the middleware, which in this case was Fmod Studio low-level API. Wouldn't it be nice if we could do this using just standard facilities? The thing is, though, the standard can't really replace Fmod Wise and ADX2, not only because of those fancy tools that I showed you the screenshots of earlier, but because the richness and the functionality of APIs is not necessarily something that we should be striving for, because they're very targeted at games. So it shouldn't, right? The standard shouldn't be in that space. But maybe the standard can provide a way to communicate with the audio device for things that need it. Before I embarked on this journey, though, I decided to see what the standard has to say about audio. And here's what I found. The standard has nothing to say about audio. It's crickets. So I decided to move toward a standard C++ audio library and think about what shape that would take. But even again, before I started there, I decided to ask why. Why should we even standardize this? And to answer that, I'm going to point at P669, which is by Guy Davidson and Michael B. McLaughlin, why we should standardize 2D graphics for C++. This is a really good summary of the 2D graphics proposal, and starting on page 8 of that proposal, there's a justification of why we should be doing 2D graphics in the C++ standard. The thing is, this paper should be templated, because if you just replace 2D graphics with audio, all the same justifications apply equally validly. So these justifications in the paper take the form of responses to potential objections. For example, game devs won't use it. If we provide this, no game in existence is going to use this. Well, you know what? Some games will. Some games will have modest requirements and just want to reach for the standard. Some games have more serious requirements, and but they're comfortable building on whatever feature set. So long as it's powerful enough, they're comfortable building on the feature set provided by a standard. And then there will be 8 libraries that people will build on top of standard facilities that will be powerful enough for games. Also, games are not the only customers. Any device with a speaker wants to communicate with audio. Think about your Google Home or Amazon Alexa device. Think about your alarm system at your home. Think about a sensor that is detecting things. Think about any device. There's tons of devices that have speakers. It's not just computers. We also have an objection that widely used libraries already solve this. We've got those three that I showed, fmod, wise, and ADX2. We've got plenty of open source libraries that do this. Why do we need it in the standard? And the answer to that is, right, the standard is supposed to standardize existing practice. This is standard. This is not anything new. We know how to build these APIs. The APIs for communicating with these devices have been stable for decades, and we know how to do it. We know how to do it right. And as you see new APIs, like I saw that Windows has a new one called Audiograph that follows exactly the same patterns. It's not exactly the same API, but it follows all the same patterns that we know and are standard and are that are in the shape of the things that we should be doing. So we should be doing this. I believe we should be having standard audio. So I came up with a set of abstractions that I think are at the right layer for the standard. And I'm going to go through all of these one at a time. First one is the device. This is the thing that is wrapping that high priority mixer thread and providing the actual wave data to that driver, filling the wave data, resolving the DSP graph, and creating the actual sound. So believe it or not, one of the interesting things about the API for this device interface is that it has to, one important part of the API is that it has to provide device selection. Most PCs have more than one output device. If you've got a multi-channel output on the back of your computer and a stereo plug on the front for your headphones, that's two separate devices. If you've got an optical out, so you can plug it at your PC into a receiver, there's another output device. You plug in your Bluetooth headphones, there's another output device. If you, there's just your PC, and if you output through your video card, through an HDMI cable, there's another output device. So PCs have tons of output devices. And then some devices have no output. So we need to provide a null driver for computers without that audio output. A voice is then a wrapper for a currently playing sound. All of this, by the way, is subject to bike shedding. I'm not married to any of these names. A voice is a currently playing sound, so it's going to have functions for things like volume and pitch and panning. I have their left-right panning. I was at the SG14 meeting last night. People convinced me that we really ought to be supporting surround panning and other interesting panning mechanisms. So pretend left-right is gone from that. And voices get their audio data from sources. Now, a source is an abstract base class that has three built-in implementations from this standard. A buffer, which is an in-memory buffer of audio data, either owning or non-owning. We have a file stream, which is a pointer to a file that is streamed into this double buffer that I talked about earlier. Now, another thing from SG14 that I forgot to update my slide, I have their IF stream, but there's no reason why that couldn't be just an iStream and get its audio data from, do this double buffering mechanism from any stream source. And the last one is a synth, which is a synthesizer where, again, it's another abstract base class where you're expected to fill in and override some virtual function that implements your own algorithm for generating audio data on the fly. And these are the boxes that we saw from earlier. These are the same boxes in the same shape, and that's where these particular implementations came from. So just those three now, all of a sudden, we have enough to load data from disk, from anywhere, play it out the sound device. We also have an effect and an effect instance. So the effect is a thing that can affect the playing audio. For example, a low-pass filter, an equalizer, a reverb. There's tons upon tons of literature on these. They're often called, it's DSP processing, digital signal processing. I just realized DSP processing says processing twice. I just realized that. Anyway, so we can make whatever algorithm we want. We implement it in an effect. We override our virtual function, and then when we apply an effect to a voice or a submix, which we'll talk about in a moment, then we get an effect instance, which allows us to apply parameters to the effect. The last interface is the submix, which takes both voices and submixes as inputs and then mixes them together. And then you can apply volume changes or any of those effects and filters, and then set it off to the next submix or out to the sound device. And this creates a graph that the audio thread has to resolve kind of at runtime. And so these submixes are very important for video games because they provide hooks for the sound designers to control the mix in a very fine-grained fashion. If we put all these things together, we get, so I'm going to show some code samples at this point of what happens when we put all these things together. This is my favorite, what I hope will be standard C++ 10-liner. Now, there's a little asterisk next to the 10. That's because I had to add those two using namespace declarations in order to make it fit on the slide, but you can pretend that all the functions are qualified with the appropriate standard namespace and then get rid of those 2 lines, and now it's 10 lines. You can also adjust the brackets and get rid of the return 0 and it becomes less than 10 lines, but you get the picture. This is the same code I showed earlier from Fmod Studio API, except using these standard facilities. Another implementation, another example, here's a low-pass filter. Don't use this code. If you're implementing a low-pass filter, please don't use this code. This is something that I cribbed very quickly off the internet. It is hard-coded to a single frequency. It assumes a fixed sample rate for your mixer, and it has pops and clicks. So please don't use this. But I just want to show, again, the shape of what this is. We have a low-pass filter. We're inheriting from standard audio effect. We're overriding this process function, and we have to fill the output buffer with valid audio data. Once we implement this, we can add a low-pass filter by taking our audio, our voice. This is the same code as before, and we add effect, low-pass filter, and now we play it with the low-pass filter. Setting up submixes. Here is a very simple submix chain. We have a master bus, our master submix. We have sound effects, music, ambience, and voice submixes. We assign those bottom 4 to the master. And now we can set parameters. We can set the sound effects bus to -24 decibels, that's 0.0625. We can apply a low-pass filter to the ambience submix. Now to play the sound through the submix, we start with the same code as before, but we assign the voice to the sound effects submix, and we get that volume reduction. We can do the same thing, apply it to the ambience submix, and now we get a low-pass filter as it passes through the chain. Now, lest you think that all of this is slideware, here is, we can all see that, yes. Here is our same code that I had on the slide, and if I play this, that's demo number 1. Demo number 2, here's our low-pass filter. This is a slight variation on the code that I showed you to remove some of the clicks. And again, the same code. Note here we are adding the effect of the low-pass filter. Again, we compile and run. Same sound with the filter applied. The demo number 3 is we're going to hear the sound 3 times. Here we're setting up our submixes. Same code as on the slides. We're going to play the sound once dry, that is without any effects, not going through any particular submix. We're going to hear it again going through the sound effects submix with a volume reduction, and we're going to hear it again going through the ambient submix with the low-pass filter. Yay! All right, so now I have to do my same little rigmarole. Let's see. Extend, yes, and then thank you. All right, I want to finish up here with a quick shameless plug for my book, Game Audio Programming Principles and Practices. This is a gem-style book. It's an edited volume full of articles from some of the best audio programmers in the games industry, available from CRC Press. And so I encourage you to go check it out. Unfortunately, it's not at the bookstore downstairs. So, at this point, I'm actually much earlier than when I practiced this, because you always talk faster during a speech when you're giving it than when you practice it. So I have about I don't know, 14-ish minutes for any questions, comments, compliments, complaints. I will be here afterwards also for anyone who wants to talk, and you can always reach me at this email address. Yes, sir.
Are you actually going to put together a proposal, or do you have one for standard audio?
I don't have one yet. I'd like to start the process. I was at SG14 last night, the SG14 meeting, and I got a bunch of good feedback from people, encouragement and good feedback, a little bit of discouragement, but people had strong opinions. But I'd like to start the process and get the ball rolling. I was told it's going to be a very long and painful multi-year process. So.
Something that I just don't know if you would also include is math utility libraries for doing decimal conversions.
Yes, for sure. Like decibel conversions, sant to pitch frequency or pitch percent conversion, stuff like that is all very valuable. I'd like to have that kind of stuff. Even if there's a desire for it, like if I get guidance in that direction, I would even think it'd be valuable to have some simple math utilities for doing like low-pass filtering and like biquads, and so some of the kind of common things that are relatively simple to implement that are not too exotic. I'd like to see just at least in a math library available in like a numeric sense. That going that direction becomes even deeper down the rabbit hole, and I just want to start with showing kind of what I have and even making sure that works. All the code that you saw, the kind of demo, I threw that together relatively quickly. It's a wrapper for Fmod. I actually wrote that as an Fmod just to make sure that the interface I had kind of made sense. But some of the details of that interface come from the fact that the low level is Fmod, and if I were to build it for real, I would have to change some of those interfaces just because the things when you're building your own DSP graph as opposed to using someone else's, you're going to end up with different kind of design decisions. Yeah.
I was actually curious about why no input device support as source, and also just wondering about like channel control over channel normalization and stuff when your audio file has 4 channels and you're on a device that only has 2, that kind of stuff.
Excellent question. So there's 2 questions there. The one is about microphone input, and the second one is about channel routing. Microphone input is not something I'm ignoring. It is something that I'm omitting on purpose because it's kind of orthogonal. You can have an audio out without having to deal with audio in, and audio in is important and it's relevant and it's part of this whole experience, but it's sufficiently orthogonal that I wanted to kind of tackle it one half at a time. I fully think that microphone input is very important. A lot of games use it, and it's a big enough topic on its own that start with one. I also had SG14. There were people who were coming up to me. You're the 3rd person who asked about microphone input, so I'm not forgetting about it. The second question is about channel routing. Or channel? Are we talking about down mixing, or are we talking about routing?
Just
all of those things. Down mixing. I haven't thought about in the context of this proposal exactly what format that would take. So I don't have an answer for down mixing. For channel routing, though, I would actually implement that as an effect, and you would have an effect that does the channel routing from 3.4 to 1.2, or however you wanted to do it. Maybe make it configurable in some way. Actually, if you look at the Fmod Studio low-level API, they have one of these, and they implement it in exactly the way I described. It's an effect that they have like 32 channels that you can route however you want. You could do like 1-1, left right goes to the same channel 4. So that kind of routing. Yeah. So, yes.
As an expert of the industry, how would you recommend studios, engineers, guys out there who have already been in the weeds making their own audio engine, stuff like that, to use the standard sound library? Would you recommend them to kind of just like table that, start again, build a new one, or somehow try and mix the standard into what they've already built up for the past 10 years, like you said?
That is an excellent question. In case the microphone didn't pick it up, the question is for people who have already got their audio engines kind of stabilized and standard. Is the intent to kind of have them start from scratch with this, or to change, or this is kind of what you're asking? That's an excellent question. I don't actually have a very good answer off the top of my head. I think my vision is if this came into existence in its fully formed and operational state tomorrow, I wouldn't use it in my games. I might use it in my personal project, but I wouldn't use it in my games because I already am using these middleware products that we've already got a license for and we're using. But as a middleware vendor, like if you're talking about Unreal Engine or Unity, or you're talking about a brand new game that didn't already have some legacy. So a brand new game, I would consider this. If the functionality is powerful enough and it's providing enough flexibility, I might use this in a new game. For an engine like Unreal or Unity or any of those other guys, it would behoove them to implement a low-level driver. They already have some abstraction layers on top. And so it's relatively simple for them to say, well, now we'll slot in standard audio so long as it has enough functionality, which, again, assuming it came into existence tomorrow in the vision that I have in my head, it would. So the standard audio interface would, in that case, become an option for people using these middlewares. Any other questions? Cool, well, thank you very much for coming. And yeah, have a good rest of the conference.